Okay, this is William Schwab. This is Lab 2, Week 2 in Robotics Mechatronics. And there's our circuit that we're going to do this week, and there's the program that we're going to put into it. And if we look over here, here's the shortened version of our program on the Arduino. And over here we've got our protoboard and our breadboard, I guess, and protoboard. And here's a resistor. When we vary the resistor, the LED duty cycle will vary with the voltage on the from the potentiometer, from the pot. And as the voltage goes lower, it goes faster and faster, and then it goes almost continuously on, and you can barely see it lit up at the bottom there. And that's about at 0 volts. So that's the first part of our demonstration. Okay, this is the second portion of the lab, and it's the same pot, and it's the same thing except we've added a couple serial lines in there to print out the serial output. And so if we go up to our tools serial monitor, we can see the output being printed out there, and that helps us quite a bit and to see what the digits in the A to D converter are going. As we go up to a higher and higher value, it gets closer to the 1023. Our LED is a long time. There's 5 volts at 1023. Our LED is very long, and if we quickly turn it down, so it's going very, very fast. Right there, it's got the A to D is running at about 16, 17. So there we have that. Okay, this is the third part of our test with just the potentiometer. And this, what we've done is we've added some more serial outputs so that we can not only see the A to D converter, but a mapping where it goes from 0 to 5 volts. And since that doesn't work because apparently it's just a truncated number, what we've got is the actual volts. And that's done by multiplying the value of the bits, which is 4.88 millivolts per bit value, times the output. And if we look at the output on the serial line, and we've also put them all on one line, so we get the A to D over here, the mapping over here, which is the truncated value, and then the actual voltage. And we're at about half a volt here, and if we adjust it, we can adjust it up to a higher value. And the truncation changes every time we hit 1 volt. So it goes from 0 to 1 right at 1 volt. Goes from 1 to 2 in the truncated value. We're at 199 and we're still at truncated. And then we go over 2 volts, we get a truncated value of 2. And so that's the way that operates. And over here we still see our LED performs the same way. Now we can also see that the onboard LED is wired to pin 13, which is also this LED, so they have the same function. So we may remove the one from the breadboard just to get it out of the way since it's kind of redundant. Alright, now we're going on to the further VEX parts. Okay, and for the first part with our VEX sensors, we've pretty much done the potentiometer first because it's the easiest one. It's pretty much a drop-in replacement for what we were doing before. And the same thing is what we have before. Now we got rid of the board, the LED on the breadboard, and we just can look at the LED on the protoboard to look at the difference in the rate it changes, since it was the same as the one on the breadboard, and there it's at a low voltage, and there it's at a higher voltage. We can also go over to the serial monitor is still up and running, and we can still see right now our voltage is at 1.4 volts and the count is at 286. It's probably impossible to read, but now we're adjusting it upwards. And as soon as we go over 2 volts, the truncated value goes from 1 to 2. And the same thing when we go from 2 to 3 volts. The truncated value goes from 2 to 3 right there at 3.02 volts. and the A to D value is 618. So that's the way that circuit is working. Okay, and here we are using the limit switch, which is going to simulate a digital input. Now right here what we've got is we've also got a pull-up resistor that runs between the 5 volts and the analog signal, so that the input is a solid input. And as you can see, it's a full range voltage, 1023, or maybe you can't, I don't know. But so the light is beeping very slow. And then when we close the limit switch, it runs off in zeros very fast. And that's because it's getting continuity to ground, so it's measuring 0 out of the A to D. And the voltage is also 0.00. And when we open the switch, it's back to 1023 and the voltage is 5 volts. Now if we look at our lights over here, we can see that the light is beeping very slow. Now what happens when you close the switch, the light goes out. The light goes out and you can't see anything. Now, you can't tell if it's working or not. That's because in the circuit, we're only lighting the light for what the D to A is reading, or A to D is reading, and since it's reading 0, it's not putting light on at all. So we can't read it at all, whereas before we saw it kind of continuous. And the only way we can tell that is when we look over here at our serial output, and it shows it scrolling really fast. The voltage is 0 and the A to D is outputting a bit value of 0 too. And when we let go of the switch, we slow down and we're at full range 1023 once again. So that's what we have for the limit switch to simulate the digital input. And there we go again. Okay, for the final exercise here, we're taking our little line tracker and we're running across the, we actually have a little test track here that we're trying to run it across, and we have the same program again, just looking at the values and whatnot. Now if we go over here, we put our LED back on so we can take a look at what's happening, and you can see we're lighting up fairly slow, which means that we're not receiving anything, any feedback from the surface. Now when we're, there we go, when we're not on target and we're actually trying to track. Now if we go over to our target here, and we'll try to get both of them in the picture. When we go over there, we start going at a slow pace, which is about 4.25 volts on average. Kind of depends on how much we're hovering above the surface and whatnot. And then when you go off the surface, it quickly drops to like a 1/4 volt and a fast dropping. But there is some intermittence in the time, and I started out by using this black, it's almost like a post-it note, and not all black materials are the same, as you can see in this one. This black one really gets the thing operating. In fact, this is only about 0.2 of a volt, so it's even more reflective, even though it's black, than the surface of the desk. So it can be deceiving. And there's what we are when we're back on track. Just a nice slow monitor. So that's that. Thank you.